Introduction to ChaChaPoly. Welcome to the channel. Please consider subscribing. I produce daily videos covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving into ChaCha20-Poly1305, a modern and high-performance cryptographic tool that keeps our data safe. You'll often see it referred to as ChaChaPoly. It's what's known as an AEAD, which stands for Authenticated Encryption with Associated Data. That's a fancy way of saying it does two critical jobs at once. It encrypts our data so no one can read it, that's confidentiality, and it also creates a special tag to ensure the data hasn't been secretly tampered with, that's integrity and authenticity. Think of it like sending a valuable item in a locked box that also has a unique, tamper-proof seal. Only the intended recipient has the key to open the box, and they can immediately tell if someone tried to mess with the seal. In our digital world, this is essential for securing everything from your web browsing with TLS 1.3 to private conversations and VPN connections. The two core components. ChaCha20-Poly1305 is a combination of two distinct cryptographic algorithms designed by the brilliant cryptographer Daniel J. Bernstein. First, we have ChaCha20, which is a stream cipher. Its only job is to encrypt the data. It takes a secret key and a unique number called a nonce, and it produces a long stream of pseudo-random bytes called a keystream. This keystream is then combined with our plaintext using a simple XOR operation to create the ciphertext. The 20 in its name refers to the 20 rounds of mixing it performs to ensure the keystream is unpredictable. The second part of the duo is Poly1305. This is a message authentication code, or MAC. Its job is to provide the integrity and authenticity, that tamper-proof seal we talked about. It takes a separate, one-time key and the data we want to protect, both the ciphertext and any extra, non-secret data, and produces a 16-byte tag. Together, they form a powerful and efficient team. Inside ChaCha20, the state. Let's look under the hood of ChaCha20. At its heart is a 512-bit, or 64-byte, block of memory called the state. This state is organized as a 4x4 matrix, where each cell holds a 32-bit word. This isn't just random data, it's meticulously structured. The first row contains 4 constant 32-bit words, often called magic numbers, that are always the same. They prevent certain attacks and identify the algorithm. The next 2 rows are filled with the 256-bit secret key. The final row is for the block counter and the nonce. The counter starts at 0 and is incremented for each 64-byte block of keystream we need to generate, ensuring that even for large messages, the keystream doesn't repeat. The nonce, which stands for number used once, is a 96-bit value that absolutely must be unique for every single message encrypted with the same key. Reusing a nonce is a catastrophic mistake that would break the security of the cipher. The engine. ChaCha20 quarter round. So, how does ChaCha20 turn its initial state into a random-looking keystream? The answer is a simple yet powerful operation called the quarter round. This is the core mixing function of the cipher. It takes 4 of the 32-bit words from the state matrix as input. Let's call them A, B, C, and D. It then puts them through a series of 3 types of operations known as ARX: addition, modulo 2 to the 32nd power, rotation, bitwise rotation, and XOR. For example, the first step is A plus equals B, then D XOR equals A, and then D is rotated by 16 bits. This sequence of ARX operations is performed several times within a single quarter round. The beauty of ARX is that these operations are extremely fast on modern CPUs, which is a key reason for ChaCha20's excellent performance without needing special hardware. This quarter round function is applied repeatedly, 80 times in total across 20 rounds, scrambling the columns and diagonals of the state matrix until the output has no discernible connection to the input. From state to keystream. Now that we understand the mixing process, Let's see how the final keystream is produced. We start with the initial state matrix filled with our constants, key, counter, and nonce. ChaCha20 then performs 20 full rounds of its mixing operations. Each round consists of column rounds and diagonal rounds, ensuring that every bit of the state influences every other bit. After these 20 rounds are complete, we have a thoroughly scrambled state matrix. Here's a crucial step. To prevent an attacker from simply reversing the quarter-round operations, the cipher adds the original, initial state matrix to this final scrambled matrix, word by word. The resulting 64-byte block is our keystream. This block of keystream is then XO-read with the first 64 bytes of our plaintext message to produce the first 64 bytes of ciphertext. If the message is longer, we simply increment the counter in the state matrix, run the whole 20-round process again to generate a new 64-byte keystream block, and XOR it with the next part of our message. This continues until the entire message is encrypted. Poly1305, the authenticator. With our message encrypted by ChaCha20, we now need to ensure its integrity. This is where Poly1305 comes in. Poly1305 is a high-speed message authentication code, or MAC, to work. It needs its own secret key, which must be used only once. Where does this key come from? We generate it using the same ChaCha20 function we've just discussed. We take our original secret key and nonce, but this time, we set the block counter to 0. We run the ChaCha20 block function just once. The first 32 bytes, 256 bits, of the resulting 64-byte output block become the one-time key for Poly1305. This elegantly links the authentication key directly to the main encryption key and nonce without exposing any information. Using this key only once is critical for security. If the key were reused, an attacker could potentially forge authentication tags for new messages. How Poly1305 creates the tag. The process of creating the authentication tag is a fascinating piece of mathematics. Poly1305 takes the one-time key we just generated and the data we want to authenticate. This data includes any associated data, for example unencrypted headers, the ciphertext itself, and finally, the lengths of both the associated data and the ciphertext. The algorithm processes this data in 16-byte chunks. It interprets these chunks as numbers and uses them as coefficients in a large polynomial. This polynomial is then evaluated at a secret point, which is derived from the R part of the one-time Poly1305 key. The result of this calculation is taken modulo a large prime number, 2 to the power of 130-5. Finally, the S part of the one-time key is added to this result to produce the final 16-byte authentication tag. This process effectively creates a cryptographic fingerprint of the message. Any change to even a single bit of the input data will result in a completely different final tag. Putting it all together, the AEAD process. Let us walk through the complete ChaChaPoly encryption process from start to finish. First, we take our plaintext message. Using our secret key and a unique nonce, the ChaCha20 cipher generates a keystream, which is XORD with the plaintext to produce the ciphertext. That is the confidentiality part. Next, for the integrity part, we run the ChaCha20 block function with the same key and nonce but with the block counter set to 0. This gives us the one-time key for Poly1305. We then feed the Poly1305 algorithm all the pieces it needs to authenticate. Any associated data, the newly created ciphertext, and the lengths of both. Poly1305 processes all this information and computes the final 16-byte authentication tag. The final output that gets sent over the network is the ciphertext, immediately followed by this 16-byte tag. We have now successfully encrypted and authenticated our message. Decryption and verification. When the recipient gets the message, the process happens in reverse, but with a critical security step first. They receive the ciphertext and the 16-byte tag. Before they even attempt to decrypt, they must verify the tag. Using the shared secret key and the same nonce, which is also sent along with the message, the recipient first regenerates the one-time Poly1305 key. They then take the received ciphertext and associated data and compute their own version of the tag using the exact same Poly1305 process. Now they compare the tag they just calculated with the tag they received. This comparison must be done in constant time to prevent timing side channel attacks. If, and only if, the two tags are identical, the ciphertext is deemed authentic and untampered. At this point, it is safe to proceed with decryption. The recipient uses ChaCha20 with the secret key and nonce to generate the exact same keystream that was used for encryption, XORs it with the ciphertext, and recovers the original plaintext. If the tags do not match, the message is considered fraudulent and is immediately discarded without being decrypted. Why is ChaChaPoly so popular? To wrap up, let's look at why ChaCha20-Poly1305 has become a go-to choice for modern cryptography. Its primary advantage is its outstanding performance in software. Unlike AES, which often relies on special hardware instructions in CPS for top speed, ChaCha20 was designed from the ground up to be incredibly fast on general-purpose processors. This makes it ideal for a huge range of devices, from powerful servers to low-power mobile phones and IoT devices. Its design, based on simple ARX operations, also makes it less susceptible to certain types of side-channel attacks, like timing attacks, which can be a risk in some AES implementations. Because of this combination of high security, great speed, and implementation simplicity, ChaChaPoly has been widely adopted in major Internet standards. You'll find it securing your data in TLS 1.3, the latest version of the protocol that protects web traffic, as well as in VPN protocols like WireGuard and in SSH for secure shell access. A practical example. Setup. Alright, let us move from theory to a concrete example. Imagine we are a client sending a request to a server. We want this message to be both private and tamper-proof. To do this, we need 4 pieces of information to start. First, the plaintext message itself. Hello server. Second, a shared 256-bit secret key that both the client and server already know. Third, a 96-bit nonce, which is a unique number for this specific message. We will send this to the server along with our message. And finally, some associated data, or AD. This is information we want to protect from tampering but which does not need to be encrypted, like protocol version numbers or source and destination headers. In our case, let us say our associated data is client to server. These 4 elements are the inputs to our AEAD process. Example Step 1. Poly1305 key generation. The first operation is not to encrypt the message, but to generate the one-time key for Poly1305. This ensures that our authentication is tied directly to our specific key and nonce. We construct the initial ChaCha20 state matrix using our shared key and the unique nonce, but we specifically set the block counter to 0. We then run this initial state through the full 20 rounds of the ChaCha20 mixing function. This produces a 64-byte pseudo-random block. We take only the first 32 bytes of this output block. This 32-byte value is now our single-use Poly1305 key. It is crucial that this key is never, ever reused with a different message if using the same primary secret key. This is guaranteed by using a unique nonce every time. Example step. Encrypting the plaintext. Now we can encrypt our actual message, hello server. To do this, we go back to our ChaCha20 state matrix. We keep the same key and nonce, but this time we increment the block counter to 1. We run this new state through the 20 rounds of ChaCha20, which produces a fresh 64-byte block of keystream. Our plaintext message is much shorter than 64 bytes. The encryption process is a simple bitwise XOR operation. We take the bytes of hello server and XOR them with the very first bytes of the generated keystream. The result of this operation is our ciphertext. If our message had been longer than 64 bytes, we would simply increment the counter to 2, generate another keystream block, and continue the XOR process. Example Step 3. Creating the authentication tag. We now have our ciphertext, but we need to generate the tag to ensure its integrity. This is where Poly1305 and the key we generated in Step 1 come into play. We prepare a specific sequence of data to feed into the Poly1305 function. This sequence consists of our associated data, client to server, followed by the ciphertext we just created, and finally, the lengths of both of these pieces of data in bytes. This entire chunk of data is processed by the Poly1305 algorithm using the one-time key. The function performs its polynomial evaluation, and the result is our 16-byte authentication tag. This tag is essentially a cryptographic fingerprint of our associated data and ciphertext, secured by our secret key and nonce. Example Step 4. Final transmission and verification. The process is now complete. The final data packet that we send over the network consists of 3 parts. The unencrypted nonce, so the receiver can use it, the ciphertext, and the 16-byte authentication tag appended at the end. When the server receives this packet, it first reads the nonce. It then performs the exact same steps we did. Using the shared secret key and the received nonce, it first regenerates the one-time Poly1305 key by setting the counter to 0. Then, it takes the received ciphertext and its own copy of the associated data, client to server, and calculates its own authentication tag. It compares the tag it just computed with the tag it received from us. If they are identical, the server knows the message is authentic and can proceed to decrypt it by generating the ChaCha20 keystream with the counter set to 1. If the tags do not match, the server immediately discards the message as a forgery. Thank you for your attendance. Please consider subscribing to the channel.